Program. Thank you very much, Lord. Right, so I've been asked to present what we do in our program to kind of a broader community. So we'll see how that goes. Before I start, let me just write down 3 words. So 3 words that, to the untrained eye, seem to be featured randomly in our conference and program. And this untrained eye would be about half right. But I'll try to my message of today, at least the story I'm going to tell is from the point of view of Spintronics. That's kind of my background. So our program brings together the community of Spintronics, quantum magnetism, criticality, and topological insulators. And so the story I'll try to tell is that, let's say, from the point of view of at least the development in Spintronics, is kind of very natural, and let's say unavoidable to bring these 3 communities together, and that's what our program is all about. But probably somebody from these other 2 communities will tell a slightly different story, but it's kind of the path I'll take. But just to get everybody on the same page about, well, since I'm going to tell it from the point of view of Spintronics, I want to kind of give a Spintronics 101, and then we'll take it from there, and then at some point I'll arrive at topology and a little bit of quantum if I have time, but I think we'll see how it goes. I do encourage the non-experts to kind of halfway also ask questions. I also do encourage the experts to just shut up, okay? And give me kind of feedback afterwards. So I'll just start with actually Spintronics in metals. For reasons, kind of for historical reasons. But also it allows me to introduce some concepts that I will need later on. So what this field is all about, Spintronics, is about using the spin of the electron, spin currents, for applications. And I will say a little bit about applications along the way, but I won't say it will not be my main focus. Let's say the long-term goal would be to make some energy-efficient devices, for example, connecting to your statement about energy. And the idea is to control these spin currents electrically. Now, so the first question I want to answer is, how do you actually get a spin current? And so let me, before answering that question, just sketch kind of a cartoon picture of just diffusive electron transport. So very simple diffusive electron transport that happens in any copper wire, say. So we have some conducting material. So this will be a non-magnetic conductor, say copper. We hook it up to some current or voltage source. And then this drives a current, an electron current through this system. So there are electrons that somehow move, scattering of impurities through this material, but somehow their net motion would be, let's say, to the right in this picture. So this is kind of diffusive, a simple-minded picture of diffusive electron transport. And so what Spintronics is now about is, okay, these electrons, make this drawing a little bit nicer. So this is using the charge of the electron. These electrons also have spin, a spin degree of freedom, and angular momentum. And let's say the spin could be with respect to, let's say, this quantization axis. Let's choose this to be our z quantization axis. The spin could be up or down. So in an ordinary conductor, there's no reason for these electrons to be spin polarized. So there are, say, as many up as down electrons. So as many electrons with spin h bar over 2, as many electrons with spin minus h bar over 2, and they all kind of move in the same way. Well, so let me draw some more impurities here. Like this. And so this would be the situation. Okay, electrons not spin polarized. Up electrons, down electrons drifting in the same way through this conductor. So if you want to attach some formulas to this, you could write down an equation for the charge current. Which would be so the charge current would be some conductivity times a gradient of an electrochemical potential, for example, a local voltage. But since both up and down electrons are the same in this non-magnetic material, you would get the same relation for, let's say, the up electrons as for the down electrons. And this tells you that, okay, the charge current, which is the sum of these two, is not zero. But let's say the spin current, which would be the difference of these two, is actually zero. Right, so in an ordinary conductor the spin current is zero just because up and down electrons with respect to some arbitrary quantization axis behave completely the same. So now the question is, how do we actually get a spin current? So maybe to the non-expert the question, how would you now live this degeneracy between spin up and down electrons? I don't want an answer from condensed matter theorists now, but from non-expert, from an astrophysicist or another astrophysicist perhaps. Anybody?
Magnetic fields.
Magnetic fields, right. You've probably seen many of these Blackboard talks.
Astrophysicists are always desperate and we always add magnetic fields.
Sure. I mean, there will be magnetic fields in this talk as well. How to live this degeneration. So let's say, so you want to kind of make spin up different from spin down, so indeed a magnetic field is would be a sensible idea, you would think. So let's add let's think about what a magnetic field does. So let's say a magnetic field on Earth. Let's say a normal magnetic field would be about 1 Tesla. So that's kind of a normal, there's already kind of a big magnetic field, but let's say this is something you can easily achieve without going to a high magnetic field lab or so. However, these electrons, so I'm talking about metals here, metal Spintronics 101. So the electrons kind of the conduction electrons are the electrons that live at the Fermi surface. They have a Fermi energy, and so this magnetic field should compete with the Fermi energy. Which is, let's say, 10,000 Kelvin or so. And then since the Bohr magneton is kind of almost the same as the Boltzmann constant, is around 10,000 Tesla. Oh, sorry. So the spin polarization you'd get by applying a magnetic field would be a percent of a percent, say, roughly speaking. Okay? So this would lead to a spin polarization of a small fraction of a percent. So this is something that's not, that doesn't give you a spin current, say. So now how you, so this is a problem, you might think. So there's one way to go around this, and the solution is now to use ferromagnets. Why? Because the exchange interaction, so this is the interaction that leads to the spontaneous magnetization, spontaneous spin polarization in ferromagnets, is a very strong interaction. I will not say too much about where it comes from. It's a combination of quantum degeneracy with Coulomb interactions. It's typically the strongest interaction we have in condensed matter. And so this leads to effective fields that can easily be on the order of 1,000 Tesla or so. And so these are not orbital magnetic fields, but let's say if you have an electron moving in a ferromagnet, then the spin will feel an effective magnetic field that wants to align its direction of spin with the magnetization. That's about 1,000 Tesla or so. Okay? And this you can use to get a spin polarized current. So how would you then, what kind of setup would you use then? So now we have a similar setup as over there, but now I have two conductors. So one of the conductors would be a metallic ferromagnet, and the other one would be my non-magnetic conductor. And then in between them is a interface. And since both of these materials are conductors, I can still drive a current through the system. But because of this large exchange field, the electrons in this metallic ferromagnet will actually be spin polarized. So here you have, say, more up electrons than down electrons that move towards the interface. And then right at this interface, this spin polarized current can be injected into the non-magnetic conductor. In this way. Okay, so this is a typical setup to get to inject from a metallic ferromagnet a spin polarized current into a non-magnetic conductor. And since this exchange field is very, very strong, you can achieve spin polarizations of, let's say, 10–50% or so. So much larger than for the ordinary magnetic field that you would otherwise spin polarize the system with. Okay, so how do you now describe all this? This is again just to introduce some concepts. So because the electrons are spin polarized in this metallic ferromagnet, you kind of have to generalize Ohm's law to. So this is nothing else but let's say a version of Ohm's law. So current is conductivity times voltage, or electric field. So in the ferromagnet, your conductivity of up and down electrons can be very different because of this large exchange field that differs between up and down electrons. And that also means that spin can actually build up, spin can accumulate at this interface. So we also have to allow for a spin-dependent voltage that can occur near this interface. So for the up electrons, we have this law in this version of Ohm's law in the ferromagnet. For the down electrons, we have something similar. So this is in the metallic ferromagnet. But then on the other side, we don't have this difference between up and down electrons anymore. Rather, there's no exchange field anymore. There's a non-magnetic conductor. So here, conductivities for up and down will be the same. But because we're injecting spin from the ferromagnet into the non-magnetic conductor, we still have to allow for a spin-dependent electrochemical potential. So conductivities for up and down are the same, but the currents and chemical potentials, the electrochemical potentials can still be different.
What do you do with the off-diagonal terms?
Sorry? You're an expert, so you cannot ask questions. Sorry?
I'm not.
Okay, well...
By proximity.
Right. So your question is, why don't you get like a gradient up times... so that's called spin drag, and those effects are typically very small in Fermi liquids. So they are kind of interaction effects that... but typically you neglect them, but they are observable with some special setups. Does that answer your question?
Why sigma could not depend on spin?
Say again?
Sigma could depend on spin too in
If you have strong spin-orbit coupling, for example, yes. Yeah, but okay. I think it's again an expert question, kind of.
I have no spin.
Yeah. Okay, so it could have that strong spin-orbit coupling, but here I'm considering, let's say, an ordinary metallic ferromagnet, iron, nickel, and let's say copper without strong spin-orbit coupling. So this, I will go towards strong spin-orbit coupling later. So yeah, it's a good question, but right now let's ignore spin-orbit coupling in this part. Okay? Apart from spin relaxation, which I will discuss now.
That kills me.
Yeah? Okay, so these are kind of the equations describing the spin and charge transport in this setup. So we have now spin currents flowing through the system, charge currents flowing through the system. And we have to now impose or solve these equations together with, let's say, charge conservation. So charge is a proper conserved quantity, but spin is not. So this means that the divergence of spin current doesn't have to be 0. And so typically in the simplest case is something like, let's say, at least proportional to the spin flip relaxation time times this difference in spin accumulations.
Rembert, I think in the first equation you also have to write some continuity equation, right? Because you already introduced some density gradients.
Yeah, okay, maybe I'm a little bit...
Otherwise, I mean, because you've written already density gradients.
Well, okay, let's...
Gradients is zero.
I mean,
If it's time independent, that's okay.
I think it's steady state,
Yeah,
right?
that was a steady state.
Steady state, yeah.
Steady state.
Yeah.
But it has to be electrically neutral. It's very hard to break electrical neutrality.
I think again we're kind of going into expert
I think they forgot about your statement of shutting up.
Doing well.
Yeah, I think it's... Anyway, okay, good. So we basically have these equations together with this one, and if you plug this into here, you get a equation for the spin accumulation. In the steady state. Thank you. That basically says that its decay is characterized by a certain length scale. This is called the spin flip relaxation length. So I've introduced here a spin flip relaxation time, and there's a length scale associated with that, which is a spin flip relaxation length. Okay, so this basically means that the spin accumulation will decay exponentially away, in this case, from this interface. So if you draw the spin accumulation, let me do that here. So let me introduce the spin accumulation mu s as being the difference between spin-dependent chemical potentials, you'll see a decay away from the interface to 0 over this spin flip relaxation length. And this spin flip relaxation length, I'd say typically would be in the order of, let's say 100 nanometer or so, or thereabouts, for a metal like copper, for example. Okay, so this also means that the spin current so let's define it as JS. So the difference in currents between up and down electron also decays on the same length scale. Okay? So you can inject a spin current. So this is now my x direction. And it lives in this part, the non-magnetic conductor, where normally it's 0. So it's injected and it decays over a length called spin flip relaxation length. Okay.
So I assume this mean-free path is also impurity dependent, material dependent.
Right. So these kind of the processes, at least in these simple systems that limit the lifetime spin, will just be let's say spin orbit coupled impurities. So a little bit of spin orbit coupling with a little bit of disorder, but nothing with strong spin orbit coupling yet. So.
What happens at the interface? Does it have some conductivity additional contribution? No?
Right. Okay. Can we just not go into all these details? I think it's somehow. The general setup is just okay. I inject. I'm saying this to you because you're an expert. So the general gist of it is okay. We have a metallic ferromagnet. There's some spin polarization that we try to inject in this non-magnetic conductor. There's some finite lifetime over which the spin then decays. A finite length scale over which the spin decays. And okay, there's many more details to discuss, like what gives rise to the spin flip length, what happens exactly at the interface, are there no spin flips? So these are all details that you can easily kind of enrich this model with. Yeah, go ahead.
So why
are you an expert or non-expert?
I would say non-expert.
Okay, good.
So my question is just, why is it important that you are trying to inject this current in the non-magnetic conductor? Why are you just not happy with saying you have a spin current in the ferromagnets?
Right, so this is kind of dependent on the applications ultimately you're looking for. I was going to go to that now. Yeah. Good question though. So I mean, one final, or let's discuss this in context of an application. So if you now want to do something with this spin current, and that kind of answers your question, I hope at least, is so if you have now, let's say this setup, so ferromagnet, still a conductor, non-magnetic metal. So I have here now a injected this spin current, but it only lives over this length scale of the spin flip relaxation length. So if I now make this part, this non-magnetic conductor, smaller than the spin flip relaxation length, I can do something with this spin current if I put another ferromagnet here. And so what now typically, this is kind of, let's say, Spintronics in the 90s. What people typically did is, or considered is, you have some ferromagnet with, let's say, magnetization direction up, and then you're interested in what happens if I put another ferromagnet here, which is then a magnetization either along this ferromagnet, it is also a ferromagnet, along this ferromagnet or opposite to it. And this then influences the total conduction of this setup. Because if the spins, the spin polarization of the current here is kind of opposite to what it wants to be in this ferromagnet, there's an extra resistance. So these are kind of typical things that people studied. This is also used in hard disk readouts actually nowadays. This is kind of an old an example of application of metal spintronics that surfaced in the late 90s, early 2000s. Okay, so this is kind of my introduction to metal spintronics, and what has happened now over the last... Did this answer your question, by the way?
Yeah.
So what has happened now over the last few years, let's see, maybe this, read this, is that people have been interested in replacing one or perhaps all of the ferromagnets in that setup there with magnetic insulators.
So Rembert, is this now used technologically in magnetic drives?
Yeah, that's what yeah, it's indeed, that's what I said, yeah. Yeah, thanks. No. So the question is, what about magnetic insulators? So this is a development over the last few years. So again, the same setup. So let's for the moment say we still have a ferromagnetic conductor here. A non-magnetic metal there. And so this ferromagnetic conductor will have some magnetization, for example, in this direction. A non-magnetic metal there, and then here's some magnetic insulator. Okay. So you can no longer hook this up to a battery. Well, you can do that, but nothing will happen. So, so this system is electrically, magnetic insulator means electrically insulating magnet. So no charge is flowing here. So there's no need to, there's no use in hooking this up to a battery in the same way as for the complete metallic situation. So one thing you could do is heat this side of the system up, for example. So you could say I just make this a little bit hotter than this side. Because somehow it's an electrically insulating magnet, but it still conducts heat. So in principle you can have a situation that you have a heat flow plus perhaps a spin current. And I don't want to say too much about this, but this is indeed possible. And this is one of the reasons why the word heat is also somewhere in the description of our program, even though I didn't mention it explicitly here. But there's a little bit more, I think, kind of exciting way of considering such setups. Which is the following. By using what's called the spin Hall effect. Okay, so let's now forget about this left ferromagnet. Consider a setup where I have a non-magnetic metal with strong spin orbit coupling. I'm just realizing I shouldn't have written this down, this inside the box. Sorry. Right, so let's say on the left side of the heterostructure, we have a non-magnetic metal with strong spin-orbit coupling, and on the right we have a magnetic insulator. And so for the moment I'm just going to consider the, let me skip that for now. So let's first look at the non-magnetic metal with strong spin-orbit coupling. So I'm not interested at the moment in heat current, but I'm interested in doing something with electrical current still. And there is actually, so there's no way I can drive the electric current in this direction, just because this is an insulator. But I can still drive a current tangential to the interface. So let's say I drive it into the board. So you should just imagine the current going into the board, so there's an interface between conductor metal, current going along the interface, okay? So that's still possible. Now if, if this material has strong spin-orbit coupling, it may host something that's known as a spin-Hall effect. And the spin-Hall effect basically means, let's say in the simplest way at least, that because of the spin-orbit coupling, the up electrons will drift, for example, to the left, and the spin-down electrons will drift to the right, as compared to this flow here. So what could happen is that the, use a little bit of space, so the charge current is going in this direction, that the up electrons flow to the right, and the down electrons flow to the left.
Question?
Yes?
Sorry, yes. Magnetic insulator, what does it mean? Ferromagnet, anti-ferromagnet, or doesn't?
Magnetic insulator, so that's actually, so these experiments have mostly been done with magnetic insulators. There are also experiments with anti-ferromagnets. So for me it means, it could be anything that doesn't conduct, which has magnetic properties at this moment. I think experimentally, of course, people are restricted. You cannot just put, I mean, these interfaces, to make them, it could be very hard in practice for chemical reasons, say. But in principle, this could be any material with interesting spin properties that does not conduct.
But what is, so what is the purpose of, so where is this going? Is it the technological advance, or is there some fundamental reason for why consider magnetic insulators?
So I'm getting there, so I hope. So ask me this question once I finish this. Yeah? So let me first start to explain a little bit about the spin-Hall effect, because it's kind of, so the spin-Hall effect actually, so I'm looking now, so this Thursday there will be a soccer match between SpinQuant and Topoquant. And I will explain now how the spin-Hall effect works in soccer. And it also should mean that anybody wants to place bets, it's kind of obvious that you should bet on SpinQuant, right? So because we know about spin and all these things. So the spin-Hall effect, kind of in soccer, is you give, what do you call this, effect to a ball. So the ball starts spinning, and then it curves either one way or the other way depending on the spin you've given it. This is through the Magnus force, so the ball influences the air around it. So this is spin-Hall effect in soccer. Well, maybe I've actually now given away our tricks to the Topological. But okay, anyway.
They're just going to run around the edge of the field.
Right. Yeah. So I think there's no way we cannot win this somehow. It's, right, so that's spin-Hall effect in soccer, and basically the.
Taken on tape, by the way.
Say again?
Yeah, it's on tape. Yeah.
I will be giving a talk at the MMM next Thursday, so I don't care about
this little clip when you say.
Well, okay, I'm not going to place bets, okay? Anyway. Yeah, so anyway, so that's the spin-Hall effect in soccer, and basically at least the phenomenology works in a very simple way, kind of the same. Right, so I've the electrons flowing into the board. One spin direction drifts kind of rightward, and the other spin directions drift to the left. So this is how you get a spin current. So the charge current into the board, and so let's say a spin current in this direction. Now, I will not say too much about the precise microscopics of the spin-Hall effect. Jairo is the expert in that. I do want to say, just to give its basic, let's say its basic law, at least in the most simple case. So, so this would be something like the spin current. And I have to generalize the notion of spin current to a tensor. So the spin current can in principle flow in 3 directions, and the spin has 3 Cartesian directions in which to point. So the spin current, and angular momentum current in general, is a tensor. So there's some index, Cartesian index, let's say indicated the spatial direction of flow. There's an index that keeps track of the spin polarization. So in the simple setups there, the spin polarization was always z direction, and it was always flowing, let's say, in the x direction, for example. But in the spin-Hall effect, it can be somewhat more difficult, so I have to keep track of spatial direction and spin polarization. And then this is basically a parameter called the spin-Hall angle. Times a Levi-Civita tensor, right, times the, let's say, the charge current. So I don't know if I have all the signs correct, etc., and all the proper definitions of the properties and the units, but basically the bottom line is that this implies that the spin polarization, so in this case the z direction that I've drawn here, and the spatial flow of the charge current, so this is into the board, and the spatial flow of the spin current are mutually orthogonal to each other. That's kind of the main...
That last index should be gamma.
Oh, sorry, yeah, thanks. Yeah, this was actually an expert comment that...
I'm not an expert.
Yeah.
Rembert, and what breaks time reversal in this case? Is there a field? Is there an external field in this setup?
There's no, yeah, I would say a driver current, right? So somehow that situation is breaking time reversal, but let's say this material doesn't have to break time reversal. Okay, good. So this is now a way to, in this structure of normal metal and magnetic insulator, this is a way now to set up a spin current that is traveling in this direction with a spin polarization in this case. Okay, and that's important because in this setup that was only possible because all these elements were conducting, and I could just run a current through it. But in that setup that doesn't work. But luckily there is the spin-Hall effect that you can now use to get a spin current in this direction. And this spin current, since it's not accompanied by a charge flow, it can actually do something to the magnetic insulator. It can flow in the magnetic insulator. So the magnetic insulator, or let's say any interesting magnetic material, or any material with some spin properties, will be able to do something with this spin and perhaps conduct it or so. So let me focus a little bit on what happens now at this interface. So let's say we have spin up electrons flowing. So I'm going to draw this a little bit. Right, well, let me just draw it like this. So we have spin up electrons flowing towards this interface. And then here is the magnetic insulator. Let's for the moment just assume that the magnetic insulator just consists of one giant classical spin that I call S, where S is much larger than 1. And this one giant classical spin, well, in principle something could happen to this classical spin if the spin current impinges on it. So what can now happen is actually that, so the electrons, there's a spin current being set up in the electronic system where the spin travels towards the interface. Now this up electron cannot travel into the magnetic insulator because there's no moving electrons on this side. But what it can do, it can actually reflect from the interface and flip its spin. So this is still consistent with the spin current that's flowing in this direction, say. Yeah? Now right here at this interface, now there's actually a problem because this process itself at the interface does now not conserve spin. So there's a spin h bar loss here, right at the interface. And let's assume that here at the interface there's no strong spin-orbit coupling effect. So somewhere this spin h bar must be gone. It must have gone somewhere. And what can actually happen is that this spin in the magnetic insulator can absorb this loss in spin h bar, so it can actually tilt a little bit upward. And if you do the counting, you see that this process now conserves spin. So there's a spin h bar flowing towards the interface, it's flipped, it's minus h bar flowing away from the interface. So this magnetic insulator has to absorb spin h bar. And this entire process conserves spin angular momentum. And so what makes this possible is actually exchange interactions at the interface. So right when the electrons move towards the interface, they feel the magnetic insulator, they feel its magnetization, and that's how these two subsystems interact with each other. Should I, by the way, shut up at 1 or at 1:15?
Halfway through.
Halfway through, okay. Yeah, okay. Okay, so what now happens is, if you work out what then happens to this magnetization in the magnetic insulator, so how it changes. So remember, this is just a classical spin. And if I compute in which direction the change in the magnetization points, so naively you might think that, I have a spin polarization that arises at the interface, and then this classical magnetic moments start processing around this spin polarization. So that's perhaps what you might think. However, that's not consistent with this spin conservation picture, because if this magnet starts processing, then it will actually keep its intercept with the z-axis, let's say, fixed, and then the total spin in this thing will stay the same. Right? And so, but this spin has to tilt, this macro spin has to tilt away, or let's say towards the z-axis, to be able to accommodate this extra h bar in spin. Now, and then if you work out, so it actually has to point in, so the change in this macro spin has to lie in the plane between, let's say, the z direction, the spin polarization here, and the plane span between the z direction here and the s here. And if you work out what that is, then you'll find that this is actually a double cross product of this kind. And now this entire process does not happen without driving the spin current. So the prefactor here is, for example, something like the spin accumulation at the interface. So the non-equilibrium spin accumulation, which itself is proportional to the charge current. Okay. And this is an example of a spin transfer torque. So this is now able to, this is a way to convert this electronic spin, so this electronic spin current, into magnetic dynamics, or perhaps a spin current in the magnetic insulator. And now I just want to, let's see. So now we're kind of at the moment where I can at least say in a few sentences what our program is about. Because we now have on the board, let's say, metals with strong spin-orbit coupling. So this I would consider, roughly speaking, the domain of topological insulators. On the other hand, we have magnetic insulators. And this could be, in this picture, any type of magnetic insulators. Could be quantum magnets, antiferromagnets, it's anything that you're interested in. And then Spintronics kind of literally is the interface between these two. So it's literally about spin currents that are injected from metals, or at least systems with strong spin-orbit coupling, into topological insulators. So what we're kind of interested in, let's say some of the questions is how you can now use the spin current in this magnetic insulator. And I may have time to give a little sketch about how that works. What you could also think about is how to probe the magnetic system with these spin currents. How does the magnetic dynamics, or let's say the magnetic structure or the phase that you're in this magnetic system, how does it influence the spin current here and the transport properties? You could think about new ways to convert spin to charge current. So actually Anton had a paper last Friday in PRL, I think, where this material here is a wild semi-metal, and then you can think about new ways to convert spin to charge. So these are kind of the things we're thinking about. And another thing that I think Victor is, for example, interested in is how the magnetic dynamics here gives rise to interactions in this normal metal. So you can also think about, there's an electron coming towards this interface. It flips its spin and gives away magnetic fluctuation, and that comes back at another point, and that induces and actually interactions in the metallic system. So these are all kind of the effects that play a role in this simple setup. Now it's not true that everybody is thinking at the program is thinking about this setup, but I think it kind of illustrates the physics we're thinking about. Now I've not said anything about, not much about topology yet, but so I think the strong spin-orbit coupling very naturally brings in topology, and this is maybe a little bit of an expert remark, but it's usually topology in momentum space. So spin-orbit coupling gives rise to spin textures in momentum space that are usually topological, and that's a significant part of the field of topological insulators. The magnetic dynamics on this side has its own topology, so the structures and the magnetic textures that you may get on this side, they can also be topological. They can have interesting topological properties, and here the two can interact with each other. And I think I will, so let's say a few more minutes, right, if I understand correctly. So let me just give one example of, at least within Spintronics, what people are thinking about that may be useful for this. And I think this will answer your question, Andrew. It was also already discussed by Jaroslav last Friday, but only the program people were there, of course.
Discuss, that's not the right word.
Sorry? Well.
Proclaimed.
Stated.
I mean, so this kind of physics, so at the interface, so spin currents that flow between metals and magnetic insulators kind of give a very natural setup for what's called spin superfluidity, which I think is kind of, it's extremely simple, and it shows also a little bit of the topological aspect. So let me just end with that. So then the setup is the following. And this would be electrical control over spin superfluidity. And so the idea would be that I have two normal metals with strong spin-orbit coupling. So both of the, so let's say normal metals with non-zero spin-hole angle, so they have a large spin-hole effect. I can now imagine driving charge currents. Hang on, I'm doing it actually in the wrong geometry. So for the setup of spin superfluidity, I have to drive actually the charge currents in this way along the interface. So now this is kind of a top view of what I discussed before. And then the electrons that move towards the interface have a spin polarization towards you, again with this right-hand rule, say, and they can flip then their spin. Okay, so they will give away a spin h bar to the magnetic insulator. So this in between is now magnetic insulator. And this spin h bar can then be absorbed and converted back into an electronic spin current with a reciprocal process, and that can be detected electrically. So the idea would be that you drive a charge current here, convert it to a spin current, then use a magnetic insulator to conduct this spin from left to right, and then convert it back into charge again. Now, why would you do this? And this probably answers your question. So the why of this would be to use a magnetic insulator with very little dissipation to get spin currents over very, very long range, say. So in the first experiments of this kind, not necessarily superfluidity, spin superfluidity, the relaxation lengths were already tens of microns without any optimization whatsoever. So I think magnetic insulators are very promising in that respect. So how does the spin superfluidity work? So spin superfluidity would arise in what's called an easy plane magnetic insulator. Which is somewhat of an academic material, because usually there are anisotropies that don't make the system perfectly easy plane, but the idea would be if you have an easy plane magnetic insulator where the magnetization wants to lie in this plane, and it's kind of fully free to rotate within the plane, then injecting a spin current will actually set up a spiral that is precessing of this kind, and this spiral will actually transmit the spin current from left to right, the dynamics of this spiral. And now this spiral is completely, let's say, so the spiral you can characterize with a phase, so just the angle with the z-axis, say, and this phase, the equation for this phase is completely analogous to the equation for the phase of a superconductor. So this is how you get something that's called spin superfluidity, which is actually kind of like classical magnetization dynamics in this way. Right, so that's what people are thinking about, the kind of things that people are thinking about in this program and are doing experiments on also. So I think I think I should end here. I think this is just one example where things could be going. Yeah.
Sorry, did you mean theta SH non-zero on the left-hand side?
Sorry, non-zero, yes, sorry. Yeah. So both of these are these metals with strong spin-orbit coupling that set up spin currents that flow towards the insulator.
I wonder, it's about this quantum computer. Is it related?
Yeah, so I didn't get to the quantum. That I actually was stupid. I should have made my title Towards Quantum Spintronics. Sure. I mean, to give a simple answer, as soon as you have any anisotropies in the magnet, if you then think about the magnet in terms of spin fluctuations, they will be, you have to deal with quantum mechanics right away somehow. So if you have any, let's say a simple magnet with anisotropy and exchange, you already have an entangled state without going to any exotic materials. But part of, let's say, the program would be to actually explore more exotic setups. But it's kind of impossible to avoid quantum. So I think it's a little bit of a vague answer. I'm not going to say how to build a quantum computer, but naturally these magnetic insulators have quantum mechanical properties that we're thinking about harvesting with these electronic leads, say.
Okay, thank you, Rembert.